Thank you, Justin, for that wonderful introduction. And it's really a pleasure to be visiting Boulder today to give this talk. The first thing I wanted to say was you all clearly followed through on my intent that if I provided cake, people would come to my talk. I think that is necessary around here to get people to come out. What I want to do is talk about some of the results from the MAVEN mission. But I'm going to do it not just by going through MAVEN results. What I want to do is talk about the history of the Mars atmosphere and what we've gotten out of MAVEN integrated with other missions. So although I'm starting with MAVEN on the first chart and MAVEN in the title, and I don't know how to say anything other than MAVEN sometimes, I really want to try to put an integrated look together at the history of the atmosphere. And I want to start, though, with why I wanted to do this talk today, because tomorrow marks the 4-year point in orbit at Mars. Orbit insertion was September 21 of 2014. Other anniversaries coming up in November is 5 years since launch, and last month was 2 Mars years of science observations. So all of these are opportunities to have cake as far as I'm concerned. What I really want to try to do is look at the history of the atmosphere. If you look at the planet today, and here are 2 images, one from Viking, one from Curiosity, we see a planet that is cold and dry. Average temperatures are 50 degrees C or so below the melting point for ice. The atmosphere is thin, less than 0.5% or about 0.5% as thick as the Earth's atmosphere, mainly CO2. And the amount of water vapor in the atmosphere is negligible in terms of what we would see in the Earth's atmosphere. All of these combine together to make a planet where liquid water is not going to be stable. It would very quickly evaporate into the atmosphere, or if it was present in large enough abundance, freeze. When we look at some of the geological features, though, that let us look into the past, we see features that tell us that this was not always the case. Features like this one in the upper left that look like a dendritic valley network system, very familiar if you've seen runoff channels on the Earth. Small channels coalesce into bigger channels running downhill. It looks like water was present. The upper right is Gale Crater, which is thought to have been a crater lake. It's an enclosed basin filled at one time with water. And up in the upper right here, up in the upper right, you can see the channel through which water entered the crater. With water having been abundant enough, the rover has seen features indicative of that in terms of chemical alteration. In the lower left is a scene from the Opportunity rover showing a sequence of sediments that have morphology consistent with having been deposited by flowing water. Water has been present on the surface. And to me, the most interesting is this one on the bottom right showing the places where minerals have been identified that require the presence of liquid water in order to form. All of these features date from the early history of Mars, older than, say, 3.5 or 3.4 billion years old. And they tell us that early in history, Mars had a very different environment than what we see today. One that was consistent with liquid water, where water was more abundant or more stable than it is today. If we ask why the early environment was different, remember this was at a time when the sun was dimmer than it is today by some 25%. So in the face of a colder sun, Mars was warmer. The only viable explanation is the presence of a greenhouse atmosphere that has since disappeared, and CO2 is the most abundant gas and the most credible gas to have contributed to that. I think current thinking is that CO2, greenhouse atmosphere, is not the only contributor to the early warm, wet environment, but it's got to be a component of any explanation. What we want to do scientifically and with MAVEN is find out where did that CO2 go, where did the water go from an early thick atmosphere. And some of you have seen this chart before because I've shown it before. There are 2 possibilities. The CO2 can go down into the crust where it gets locked up in carbon-bearing minerals, or it can go to the top of the atmosphere where it can get stripped away by the sun and the solar wind and lost to space. MAVEN was designed to try to determine the role of the second one, the role of loss of gas to space, whether that was an important process or perhaps the dominant process in evolution of the atmosphere. What I want to do today is try to track the history of CO2. This is important for understanding the evolution of the atmosphere, the evolution of habitability by microbes, and the history of the planet. And if we're going to track the CO2, we can't just follow carbon or CO2. We have to follow the carbon and the oxygen separately because they can escape to space and move around, go to the crust in different ways, in different abundances. And since oxygen is also a component of water, we have to track the hydrogen and the oxygen together as well. So if we're trying to understand the atmosphere, we have to look at, and the history of CO2 and water, we have to look at it as a coupled system and track the C, the O, and the H. And you're going to see this theme coming back throughout the talk of, we can talk about loss of water. What does that tell us about loss of CO2? How do we go between the different gases to try to understand what's happening? And I am going to start with MAVEN results, but after I go through some of them on escape to space, I will integrate it more broadly. And I'm going to start with hydrogen. Hydrogen is produced, it comes from water. It's produced by photodissociation of water by ultraviolet photons from the sun. On the left, you can see an image from the IUVS instrument on MAVEN showing scattered sunlight off of hydrogen in an extended corona. The corona's seen all the way out to more than 10 Mars radii away from the planet. This allows you to calculate the escape rate. We can't measure it directly, but we can measure the profile and the abundance and calculate it. And in the right here is shown the column abundance of H, which is proportional to the escape rate. And what MAVEN has seen and confirmed from earlier measurements is that the escape rate varies throughout the year by more than an order of magnitude. When I first saw this graph, it jumped out at me that the greatest loss rate was not necessarily near perihelion. It is near perihelion, but that wasn't the driving factor, but that it was the dusty season. And Mike Chaffin demonstrated that dust in the atmosphere can enhance the escape rate. It raises the middle atmosphere temperatures. The water can move higher up in the atmosphere where it can be more readily photodissociated. And once photodissociated, the hydrogen is closer to the exobase where it can populate the corona and escape. So it makes sense. What this does do, though, in addition to helping us understand the seasonal cycle, is it says we're going to have a really hard time extrapolating the hydrogen loss through time because it's not a constant at the present epoch. It depends on things like season, distance from the sun, the amount of dust in the atmosphere, the temperature, presumably the amount of water in the atmosphere. It's going to make it hard to extrapolate. That won't keep me from doing it, but it's just going to be hard to do. And we'll come back to that. The photodissociation of water also leaves oxygen behind, and oxygen can escape by a number of mechanisms. The largest single mechanism is the dissociative recombination. If you have an O2 molecule where the O comes from water or from CO2, we don't care. For this slide, we don't care. We will care tremendously. If you have an O2 molecule, EUV can be absorbed by it and it kicks off an electron, it ionizes it. When the electron and the O2 ion recombine, that energy is released and it's enough energy to split the molecule in half and send each one off with a velocity greater than the escape velocity. The one that happens to be pointed upward, if it doesn't hit anything, will be lost to space. MAVEN makes measurements that allow us to calculate what that loss rate is. And you can see that in the top panel as a function essentially of time throughout the mission. And it seems to be jumbled all over the place. But that's because the orbit is evolving throughout the mission. If you organize it by the solar zenith angle, which is the angle relative to pointing straight at the sun, so 0 is back at the sun, 180 is the other direction, you get a much simpler type of curve, the loss rate is greatest on the day side at low solar zenith angle. That shouldn't be too surprising because the ionosphere is present on the day side because that's where the EUV photons can ionize the gas. There are very few EUV photons on the night side, so the escape flux, the intensity of the ionosphere, the escape flux drops off. In addition to that, superimposed on this, you can see a dependence on the EUV flux from the sun, shown here in the colors, where this yellowish color is the highest EUV, and that's all up at the top. The blue is the lowest, it's at the bottom. So you can see a dependence not just on solar zenith angle, but on the EUV flux. That's going to be important for extrapolating to other epochs as well. If we calculate the average escape flux of oxygen, I'm going to give it in units that make sense to me rather than per square centimeter. And that is that you would remove all of the oxygen in the atmosphere if we could strip it out of CO2 in about 300 million years. So think of it as 6 millibars in 300 million years. That's just a figure of merit to compare. That's not where the oxygen is coming from. That's not what the source is, but it helps us understand the significance of escape. The second mechanism for removing oxygen that I'll talk about is pickup by the solar wind, by the magnetic field of the impinging solar wind. The solar wind, as it's coming out at 500 or so, 400 kilometers per second, has a magnetic field. The moving magnetic field generates an electric field and accelerates oxygen ions. You can see them being accelerated upward toward the pole in this graph. These are sorted by the direction of the magnetic field, so all that acceleration in this frame of reference is always up. It creates this thing that looks like a polar plume. Draped fields being dragged over the planet drag stuff downward. We can calculate the escape rate by adding up everything we see that is escaping, and we get an amount that is less than the dissociative recombination loss by about a factor of 10. I think it's instead of 300 million years, by a factor of a few. Instead of 300 million years, it would be a billion years plus to remove all the oxygen in the system. In addition, you can see some ions being accelerated up toward the planet, and those can hit the atmosphere and knock other stuff out. That process is called sputtering, and we can calculate the loss rate due to sputtering. This is just a cartoon that shows that as the solar wind comes in, it picks up the ions, slams them into the planet, and knocks stuff out. The figure on the right just shows the coverage we've had early in the mission. And we can calculate the loss rate from this process as well. It's a much lower loss rate still. It would take more than 4 billion years to remove the equivalent amount of oxygen in the atmosphere. The key is that by looking at the individual processes and understanding not just the loss rate today, but how the loss occurs, what drives it, we can extrapolate to other epochs. And what we want to do ultimately is determine the integrated loss through time. Before we do that, though, I want to look at the loss today and ask whether the oxygen and the hydrogen are being lost stoichiometrically as water. Is the H rate twice the oxygen loss rate? This was proposed by McElroy back in the 1970s because of feedback between the oxygen and the hydrogen loss rate. And we have the ability now to add it up and calculate. At the top is the oxygen loss by each of the different mechanisms: ion loss, photochemical loss, sputtering, and then the total oxygen loss. At the bottom is the hydrogen loss. The top bar is the MAVEN results. The range from minimum to maximum is a seasonal variation. The same thing observed by Mars Express, by HST, Rosetta, Mariner 6, 7, and 9. Observations using the LASP-produced ultraviolet spectrometer. I wasn't clever enough to plot these on the same scale. There are limits, apparently. And I tried to, you guys know all the limits, but I find them out when I get up and try to produce a figure like this, where I want to compare these things. So I had to take twice the oxygen loss rate, the red in the upper figure, and show where it would be in the bottom figure. And at least twice the oxygen loss rate is in the range of the hydrogen loss rate, which suggests that they could be in the ratio of 2 to 1. It isn't right where the average is, but you could argue that it's close enough. The reason you might expect them to be 2 to 1 is because of this feedback between loss of hydrogen and loss of oxygen. The reasons you might not expect them to be 2 to 1 are the time scale to get to this equilibrium. The time scale for these things to balance is as long as 10 to the 5th years. And on that time scale, everything in the system varies. The amount of water in the atmosphere, the amount of oxygen, hydrogen in the corona, the amount of dust in the atmosphere varies on not just annual and interannual timescales, but decades and centuries-long timescales. So we don't know, given the role that dust plays in controlling the hydrogen loss rate, we don't know if what we've seen is representative of the last 10 to the 5th years. We don't know what the dust history in the atmosphere has been. So right now, I think we have to say maybe they do, maybe they don't today. Even if they do balance today, does that mean they balanced over the 10 to the 8th, 10 to the 9th year time scale so that water would be escaping and CO2 isn't? That's a question that is an open question. We now want to take these results and try to extrapolate back in time. We can do that with the history of the solar EUV flux and the solar wind. We know these from looking at behavior of sun-like stars, and we can model what the history would have been and what the escape would have been going back in time. I haven't done the models, but a bunch of people have, and I've picked one of them to show how these processes vary going back in time. They go up by 2 to 3 orders of magnitude. So the current loss rate of 2 to 3 kilograms per second can go up by a few orders of magnitude some 4 billion years ago when the sun and the solar wind were more intense. If we then integrate that up and ask about the total loss of oxygen and of water, if we look at the if we look at the loss of oxygen, if it's all coming from CO2, it's about 0.8 bars of CO2. And this isn't through all time. This is from 4.2 to 3.7 billion years ago. So it's a short time, but that's when we infer the climate was changing from the geology. If the oxygen is coming from water, it's the equivalent of a global layer of water a couple of tens of meters thick. So you can see it's an important question. Was the oxygen coming from water or from CO2? If it's coming from water, the hydrogen can escape easily. If it's coming from CO2, where did the carbon go and how much of it escaped?
Bruce, could you go back one slide a second?
Apparently I can.
Why is there a change 3 billion years ago? Change in slope?
These models are calculated by taking the behavior at certain specific ages and then just drawing a line between them on a log plot. So they used a point here, here. I think there was one here and here. So that's going to produce artificial kinks. I think the presence of those kinks is not inconsistent with the level of fidelity in our understanding of the history. But wait, there's more. Because not only is gas lost by these processes, but the sun emits solar storms that have their own effect. And this is an example of one that I just pulled off the web. It's from Soho from 2013. It's a time sequence. You can see this eruption sort of at about 11 o'clock relative to the center of the sun, getting bigger. One of the goals of MAVEN was to see if we could observe any solar storms and see what the effect on the loss rate to space would have been. See what it is, what it was. See what we observed it to be. How about that? And we could identify, we've identified many tens of small solar events, and we can look at what it does to the loss rate. It's very hard to calculate this, though, because the loss can occur into all 4 pi solid angle around the sun, but MAVEN as a spacecraft orbits in one plane at one time. And the way we calculate these, we look at what is happening when MAVEN passes through a sphere of radius about 1.5 rm centered on Mars. That's to avoid, if we counted up throughout the orbit, we would be multiple counting many things as we cross the paths of many of the escaping atoms. So we only get a couple of points, and that doesn't do justice to it. Statistically, though, we can do this. Every dot here represents a solar event. The outward going flux is plotted as a function of the solar zenith angle. The histogram black bar represents the average over the Mars year that MAVEN observed, and each dot represents the effect of one solar event. It's a log plot, so even though it looks like the average of the dots is on top of the black line, the stuff that is higher wins out over the stuff that is lower. If you do this quantitatively, the average effect is a factor of a couple increase in the loss rate. So this demonstrates that the solar events enhance the loss rate, but we haven't plugged in the strength of each storm. We can take the other approach, and that is to look at a single event and do a case example and see what happens. And we did that with an event that occurred on September 10th of last year, so just over a year ago. This was the biggest event that MAVEN has seen, and we've been able to look at it in great detail. This event was also seen by other spacecraft at Mars. It was seen by every spacecraft at Mars, and it was seen at Earth as well. This figure in the middle comes out of the Goddard modeling group. It shows the sun at the middle, Mars over here, Earth over here, and this big red blob is the event as it propagated out into the solar system. It actually hit Mars and Earth both on opposite sides of the sun. We put together a special collection of papers on the impact at Mars. There's a parallel collection on the impact at Earth. We have 2 observations that told us this was there. One was from stereo A, located here. You can see the event going off on the left. The other is from in orbit around the Earth. You can see the event going off to the right. There are different places, so you get different perspective. We had the ability to see this event in detail, and we caught it in all of its glory. I've pulled out here the key measurements. At the top is the solar irradiance. It's sort of faint, but you can see this big spike going up and lasting for a brief time, corresponding to the flare. The very energetic protons that hit Mars within just a few hours. The lower energy ions and electrons that hit Mars. The derived solar wind pressure, which goes up corresponding to the peak in the energetic ions and electrons. And at the bottom, a little hard to interpret, so I drew in a line to guide the eye, the altitude of the magnetopause. So the bow shock, the whole thing gets draped. I want to be careful to not use the wrong words. The whole thing gets compressed during the event when the solar wind has the greatest pressure, and then it expands back out. So we caught the entire event. To give you one example of what an event like this can do, I stole this from Nick Schneider and the IUVS observations. It shows the global the global aurora produced by the energetic particles hitting the planet. On the left is just before the solar event, and the speckling you see is essentially all noise. If I look, I can almost imagine I'm seeing the limb of the planet, but it's really faint. On the right, at the peak of the aurora, showing the full intensity. These things have global scale impact and effects, and it's easy to imagine that it would have an effect on the integrated escape. We can do that, but again, we have the problem that the escape is being measured from one spacecraft in one plane, and you can't measure all 4 pi directions. For this event, unfortunately, the spacecraft was at that solar zenith angle where there was the smallest effect. So we don't see a big effect in the escape. However, we can use those measurements to validate the models of the solar wind impact with the upper atmosphere, and then use the models to tell us what the escape rate has been. And that's what's shown in this figure, showing after the event hits a factor of 20 increase in the loss rate integrated over all 4 pi. So that's a significant increase. The reason this is important is that early in history, the sun may have been spitting out these events essentially continuously. So this may in fact have dominated the total loss of atmosphere to space. So far what I've done is to give you a plausibility argument that the sun and the solar wind can have removed a lot of the atmosphere. The number I gave you of as much as 0.8 bar, which based on this may be a lower limit, is a plausibility number because it depends on what's in the atmosphere. If there was no gas in the atmosphere for some reason, no matter what you do, you don't strip anything away. So there are a couple of things we can do to look at not just what could have happened, but what did happen. And I'm going to start with the argon measurements. The argon is a great indicator of loss to space because the lighter isotope, if you look at argon 36 and 38, is removed more efficiently. And the more gas that is removed, the more enrichment you see in that ratio of 38 to 36. The reason the lighter one is removed is that when you get above about 100 kilometers, the atmosphere is no longer well mixed, and each gas separates out according to its own scale height. Argon 36 is lighter than 38, so it has a bigger scale height. And at the altitude around 200 kilometers where gas is removed, it's relatively more abundant, so it's removed more efficiently. We can use the MAVEN measurements of the structure of the upper atmosphere to tell us how much more efficiently, and use that to model the integrated loss. That's shown on the right here, where each dot represents one orbit, the properties that we can measure in the upper atmosphere, and then the model relating that to the loss. The average of these is 66%, telling us that 2/3 of the argon that was ever in the atmosphere has been lost to space, stripped away by the solar wind. Right away, that tells us that loss has been a major process in the history of the atmosphere in causing atmospheric gas to be removed. CO2 can be lost by the same process as argon, sputtering by pickup ions. But as we've talked about, CO2 has other loss processes. We can also look at the carbon isotopes to tell us directly about the carbon loss. And I don't have a cool figure the same way, but we see an enrichment of the measured 13 to 12 ratio of carbon in the atmosphere is plus 46 per mil. That means it's enriched by 4.6%. Relative to the starting point, it's enriched by about 6.5 to 7.5%. And you can relate that to the total loss to space. When you sort of eyeball an estimate of the history through time of outgassing and loss to space, you get about 75% of the carbon must have been lost to space. The formation of carbonates fractionates the other way, so if there are significant quantities of carbon-bearing minerals, the loss would have been greater. So right away here, now we see that loss of CO2, loss of carbon, has been a major process in the history of the atmosphere. So the conclusion from this, and this is where I'm going to start to transition away from just MAVEN, but the conclusion is that loss to space has been a major process in the evolution of the Martian atmosphere and the evolution of the climate. And what I wanted to do now is go into the history of CO2 and see if we can construct a global inventory of all the CO2. This is where all the CO2 from an early thick atmosphere could have gone. And we've really talked about how much has been stripped away to space. I think the number based on the carbon isotopes is more than 500 millibars equivalent, perhaps much more, but certainly more than that. I haven't talked about these others. I'm going to go through them very quickly, not to get bogged down in them, but just to give you an idea of where these numbers come from. The first is impact ejection to space. All the impacts that leave behind the impact craters on the surface can eject gas to space, and you can calculate from the number of impacts we see how much gas has been lost. Dave Brain did this in a paper 20 years ago when he was a grad student, before he blew me off and did a PhD thesis with Fran Bagenal instead. But I got even with him. I got him back working on MAVEN. The model suggests that between 50 and 90% of the gas that was present at the time would have been lost to space. So again, this is another major process in evolution of the climate. The second is whether there's CO2 sequestered as ice in the South Polar Cap. Until recently, people thought the answer was no, that there was only a thin veneer of CO2 ice at the surface. Using radar, they've discovered buried deposits of CO2 ice, and you can calculate the volume. If all of that gas were put into the atmosphere, it would be the equivalent of about 6 millibars. It would double the thickness of the atmosphere. Important to track, but not terribly significant in the scale of losing a bar or two. Another possibility is whether some of the CO2 could be locked up in a CO2 water clathrate hydrate. This is a structure when ice forms in the presence of CO2. Instead of forming these tightly bound, close-in molecules, the water forms a cage structure, and the CO2 can rattle around inside that cage. There are no observations requiring clathrate to be present, but they could be there. There's an upper limit of about 150 millibars. That's a far upper limit. A much better number is close to 0 or 0, because we don't know that there are any. But if we're tabulating the amount of CO2, we have to keep track of this. The next one is CO2-bearing minerals in the crust. I talked about the formation of carbonates out of CO2. For 30 years, the holy grail of Mars exploration was looking for the mineral deposits that had to be there to retain that CO2 from an early thick atmosphere. This marks all the locations where CO2-bearing, sea-bearing, carbon-bearing minerals have been found. A few of them are near the surface, enough to hold about 12 millibars of CO2. Some of them have been identified as deeply buried CO2 exposed by impact craters, for example. It's very hard to quantify how much there could be. It could be as little as the equivalent of 10 millibars or as high as a bar. Let's see, I think the last one I have as a sink for CO2 is gas adsorbed in the regolith. The molecules, individual molecules, if they hit a grain of dirt, will stick, and they'll jump off again, but there's a steady state, a dynamical steady state abundance of molecules that are there. You can measure in the lab how much would attach, and the best estimate is that this adsorbed CO2 would hold the equivalent of about 35 millibars of CO2. We've been talking about the sinks. I can't leave this without talking about sources, because volcanism is a process that puts gas into the atmosphere. It's been active throughout history. A couple orders of magnitude less volcanism than on Earth or Venus, but probably still active today and still pumping gas into the atmosphere. It's an amount of gas that it would take about 10 million years at the rate we think it's coming out to double the pressure in the atmosphere. And most of that gas is water rather than CO2. So it's not a big source of CO2, but if we're tracking volatiles, we need to keep track of it. So let me come back to this chart, which is the global inventory, and you can see now where the CO2, has gone. The biggest single processes on this are impact ejection to space and stripping by the solar wind to space, together accounting for probably more than a bar of CO2. The biggest uncertainty is how much CO2 might be locked up in the deep regolith. Together, though, if you add these up, you can account for a thick, early CO2 atmosphere that would be necessary to produce the greenhouse warming that we saw. So that takes me up from the past atmosphere and the present atmosphere. And I want to talk now in the last 10 minutes or so about the future atmosphere, because you all know that Elon Musk and Buzz Aldrin have been talking about the possibility of terraforming Mars. I have this quote from Elon. You need to live in a dome initially, but over time you could terraform Mars to look like Earth and eventually walk around outside without anything on. I think he means without a spacesuit on. But you know, he's sort of going off the deep end, so maybe that's not what he meant. It's a fixer-upper of a planet. Terraforming is the idea of changing the atmosphere in a way that would increase the pressure so that maybe we didn't need to walk around with spacesuits and pressure suits, but maybe just jackets and the equivalent of scuba gear, breathing apparatus, and changing the temperature so that we could allow liquid water to exist. If we could do that, we have the possibility of farming, of really living rather than just going and living in a bunch of Winnebagos. Winnebagos. Try to pronounce it right. If we ask how much gas we need to do, this shows the average temperature if you start pumping gas in, go from around 220 Kelvin today to get up to melting. 273, you need a little over a bar of gas. What's the minimum temperature you need in order to have terraformed it? Unclear. I picked a number like 20 degrees lower, and that puts us into the 3/4 of a bar range. Can you terraform Mars? With the gas we talked about, with it locked up in the different places on the planet, is it possible to mobilize that gas and put it in the atmosphere and get enough out that you could raise the pressure and temperature? Sorry, I don't mean to leave you hanging there. I did bring a sample of water in case you've never seen it. So where might the CO2 come from? And I'm just going to run through the same places that we talked about on that chart. It can come from the polar caps. That's 6 millibars. That would double it to about 12 millibars. Ain't going to do it, but that's the easiest one to get out. In fact, it's the only easy one. Elon Musk talked about nuking the polar caps. The heat would evaporate, technically sublimate the CO2, put it into the atmosphere. That he got right. You could do that. The second is getting it out of the ground where it's adsorbed. The amount of gas is probably of order a few tens of millibars. I gave the number 35 millibars, and that's probably not too far off. It's really hard to get that out. It's distributed over the entire volume of the regolith and the crust down to perhaps 10 kilometers. So if you want to get it out, you've got to heat up the crust, heat up the surface, and let that thermal wave penetrate into the subsurface. That can take 10,000, 100,000 years, and you've got to heat it up anyway. So if you needed to do that, you're done. And you only get out 35 millibars. You can get it out of CO2-bearing minerals. The problem with this is that you need to heat it up to what's called the decrepitation temperature of the mineral, where the CO2 jumps back out of the mineral state into gas. If I remember, that's around 350 degrees C. So it requires more heating than you can get from sunlight unless you have a concentrator. It would require strip mining. And if you strip mine in the one region where the most carbonates are, you could get out maybe 12 or 15 millibars. If you want to get out all that deeply buried stuff, you've got to strip mine down at 10 kilometers depth throughout the whole the whole planet. So if it's there, if there's that much, it's really hard to do. And you can get it from continued outgassing, but as you saw, the volcanic outgassing rate is low enough that it's going to take 10 million years even to double the amount of gas in the atmosphere, and most of that isn't going to be CO2, so it doesn't do you any good. This, by the way, was the suggestion of the current NASA chief scientist, Jim Green, who said, well, all you need to do to terraform Mars is put a giant magnet upstream of Mars so it deflects the solar wind, and then outgassing will quickly replenish the atmosphere. He's clearly an astronomer because quickly means 10 million years or longer. I don't think it's that easy. So can Mars be terraformed? If we want to do it using technology that we understand and know how to use, I think the answer is no. It's just not possible. There's not enough CO2 available, and even if there was, it's really hard to mobilize it and get it into the atmosphere. You can always terraform Mars, however, by inventing new technology. For example, people have talked about manufacturing high-efficiency greenhouse gases that would very effectively trap the heat. That would require a pretty significant manufacturing capability at Mars. And since we haven't sent anybody to Mars, and we haven't sent anything larger than a Mini Cooper to Mars, I think that's way off into the future, far enough that I think we don't understand the technology. The best suggestion I've heard so far is to take all the excess CO2 from Venus and put it on Mars. But that has its own problems. And I'm going to come back to one of the great philosophers of our time, Calvin and Hobbes. Calvin walks in and says, "So long, Mom. Hobbes and I are going to Mars to live. Earth is too polluted." Let me just remind you that when it comes to terraforming, it's a hell of a lot easier to terraform the Earth than to terraform Mars. Earth right now is really close to an environment that we like. It's not too far off. All we have to do is stop releasing CO2 or stop polluting or something like that, and we can get our wonderful climate back. Mars has an atmosphere that is 0.5% as thick as the Earth, temperatures that are 50 degrees off, and global dust storms that kill spacecraft, apparently. It would seem a lot easier to figure out how not to muck up the Earth's atmosphere. So I think if we look at human missions to Mars, terraforming is out. I think we're going to be living in spacesuits. Here we see Mark Watney living alone in his spacesuit out on the surface. I think that's where we are. I've got just two more charts here. One is to come back to MAVEN because I want to emphasize that we've been in orbit for 4 Earth years. We have 2 Mars years of science measurements, but every year is not like every other year. And by continuing to observe, we'll see different drivers, whether it be the atmospheric water or CO2 cycle or the dust cycle. Plus, we've only seen part of the 11-year solar cycle. We got to Mars just after the peak, so we've seen the declining phase. We're pretty close to solar minimum. We'd like to see the increasing phase of the solar cycle and see it at solar max. And Frank, if you could arrange for this upcoming solar max to not be as wimpy as the last one, I think the rest of the MAVEN team would really appreciate that. Plus, we have the trace gas orbiter in orbit at Mars, which gives us coverage of the entire column of atmosphere from the surface all the way up to the upper atmosphere, interactions with the sun and the solar wind. Plus, in 2 years, we're going to be launching the Emirates Mars mission, which will be exploring, in particular, the coupling between the lower atmosphere and the upper atmosphere. And these are going to provide measurements that are really going to help us to better understand the behavior of the upper atmosphere. The last chart I want to show is a picture that you've already seen if you saw the cake before it got cut. It's a picture we're releasing tomorrow on the 4-year anniversary as part of a web release. And that's the MAVEN spacecraft selfie, taken using the IUVS instrument. It's mounted at the end of its own selfie stick, which is a 1.2 meter boom with two gimbals on two axes, so it can rotate to observe Mars. It turned out we could also rotate it back to observe the spacecraft. And I believe this is stitched together of, Justin, is it 21 separate images? To do this, there are places we couldn't image because the gimbals don't cover all angles, but you can see the body of the spacecraft, the thrusters in the lower left and lower right, the electric communications antenna that allows us to communicate with rovers, the booms supporting the Langmuir probes, one on the left, one on the right. These stick out the far end of the spacecraft like rabbit ears on an old TV. The tip of the high-gain antenna communicating with the Earth, and the tip of one of the wings of the solar panel just past where the solar panel ends. You can see the diving board here that supports the magnetometer and one of the sun sensors. There's another parallel thing on the other side. And you can see the shadow of the boom right here. And you can see the shadow of the IUVS instrument. So I think this is the first relatively complete selfie taken by an orbiting spacecraft. I wouldn't swear to that.
And the first one of any spacecraft in the ultraviolet, I think.
So this is actual ultraviolet. You haven't tried to add color, Nick?
It's not very colorful.
So it's either black and white or color. Take your pick. We're going to release this. All I can say is 4 more years. Thank you. Yeah.
So Mars used to have like intrinsic magnetic field. So when did that disappear, and what do you see like the loss of the atmosphere due to that?
We know that Mars had a magnetic field because we can measure the imprint it left on the magnetic field of crustal materials as it cooled. And by looking at regions of different ages and looking at where you have a transition from having that imprint to not having that imprint, you can date when the field disappeared. It was probably about 4.1 billion years ago. The best guess is that the turn off of the magnetic field would have allowed the turn on of stripping by the solar wind. That's the standard wisdom. It's a very glib answer, and it's not clear if it's correct or not, because the Earth is losing gas to space, even though it has protection from a strong global magnetic field. I think that's going to be one of the areas that we're going to focus on for the next couple of years, trying to understand escape from Earth, Venus, and Mars having completely different boundary conditions.
Thanks.
Yeah?
What sort of volume of water ice in the form of a comet would be necessary to create 1 or 2 bars?
If you wanted to create a bar of CO2, you would need 1 million kilometer-size ice cubes of CO2 ice. So a million ice cubes, 1 million kilometer-sized comets. But remember, most comets are primarily water ice. So to get the CO2, it's really hard. And besides, you destroy the planet with 1 million impacts. Steve?
The aspect of the dust and its impact on the atmospheric loss processes, that's an interesting monkey wrench. If you consider Mars history, astronomers know, say, for the last 50 years, how well can someone run an atmospheric model and predict when and how severe a dust storm erupts?
The problem is that we don't understand the mechanism that causes global dust storms. Every year when Mars is near perihelion, we see local and regional scale dust storms. And every 2, 3, 4 Mars years, one of those expands into a global scale dust storm. We don't know why. In addition, we've seen a lot of global dust storms over the last 60 years, 60 plus years. When the 1956 dust storm happened, it totally took the old astronomers by surprise. They'd been watching Mars for 40 and 50 years. They were old men. They had never seen anything like that in their lives. The evidence suggests that the dust behavior has changed dramatically. Not only the dust storm, but the background level of dust seems to have changed from the late 1800s, early 1900s to the last couple of decades. So fundamentally, even if we can say what the effect of dust is, we don't understand what caused it to change. We don't understand what type of behavior might be representative of the current epoch, or whether variability is representative of the current epoch. Again, that's what makes it hard to extrapolate into the past, this lack of understanding. As you know, Mars is in the declining phase of one of the biggest global dust storms in a long time right now. It peaked about a month and a half ago, if I remember correctly. And it's the best observed dust storm in history, with atmospheric measurements and upper atmospheric measurements. And I think over the next year or so, we're going to see a lot of results come out that help us to understand dust behavior. There's a special session at AGU, a late breaking session, where I think the community is going to see those data and the analyses for the first time. As an aside, who went out when Mars was at opposition about a month ago and looked at Mars? You are never in your life going to see Mars as bright as that again. And the reason is, not only was it at opposition, so it's as close to the Earth as it gets, it was a perihelic opposition, meaning Mars was near perihelion, so it's closer still. But most importantly, it was a global dust storm, and that bright dust in the atmosphere obscured all the dark stuff on the surface. So the albedo of Mars was about twice what it normally is. You're never going to see it that bright again. When I went out and saw it, I was just blown away, because I've seen Mars at perihelion, and this was so much brighter. Dan?
You've made arguments why terraforming Mars won't work. Have the arguments that you've made changed the views of those who were arguing for terraforming?
I haven't spoken with any of the pro-terraformers, but I did see their tweets when we put out a press release. Christopher Edwards and I published a paper about a month, 6 weeks ago on the terraforming analysis with the conclusion that I gave you. And we put out a press release because we thought it would be fun. We did this paper sort of as the anti-Elon Musk paper, because he's been talking so much about how easy it is to terraform Mars, and the Mars science community thought that was silly. So we wanted to put it in writing. And Elon tweeted out that he disagreed with us, that in fact he thought there was much more CO2 absorbed in the regolith than we accounted for. And clearly, to me, I don't expect Elon to keep up with the Mars science literature. But one of the systems engineers working for him on BFR is a woman who used to work with Chris McKay at NASA Ames doing terraforming. And I've talked with her, so I presume that's the conduit for information, and that some of this was coming from Chris McKay. I don't know that. I'm speculating. I disagree with that conclusion. We opted not to put out a tweet saying you're wrong, A, because I didn't want to be the next pedo guy, and B, because we had used 4,000 words to put our argument forward. I didn't see the value of another 280 characters. Plus, I think this is a scientific debate and discussion and belongs in an appropriate scientific forum rather than in the popular press. I say that despite the fact that we put out a press release. As an aside, I talked to a bunch of reporters when we put out this release, and one of them, we'd arranged a time to talk, and I answered the phone. He goes, "How are you?" I said, "I'm great." He goes, really? Even though you've dashed the hopes of thousands of science fiction nerds everywhere? And I said, what do you mean, because of that? And then I begged him not to print that. Other questions? Yes?
Okay, well, I know that the magnetic field and its importance in protecting a planet has come into question, and it sounds like it's gone the way of Pluto being demoted and everything. But doesn't the solar wind getting closer to a planet, having it be closer, get everything more energized more so than it would at a distance? Because, with all the draping, the magnetic reconnection with the crustal fields, doesn't it go in deeper, closer to the planet, get it excited? And then also, as I understand from one of the article I read that you wrote in Science and Telescope, Sky and Telescope, but about the exosphere being hotter and closer to the planet on Mars than it is on Earth. Don't all those things together aid in atmospheric loss?
That's the standard wisdom. And it's being questioned because on Earth, even with the strong magnetic field and the solar wind being stood off at a greater distance, as it sweeps by, there are still open field lines connecting the Earth's atmosphere to space, up which ions can travel and escape, and they're seen to do that. So I think, although you've described what I've thought is correct for 20 years, I think that's coming into question. And I would say we don't understand it, and I'm looking for the greatest increment to that understanding to come from studying the Earth and seeing what's happening there. Nice shirt, by the way.
Oh, thanks.
It has the MAVEN logo on it. Just before we quit, I just want to thank Nick and Justin for tremendous effort both in assembling the image and in planning the observations that carry this out. It's a lot of work, and it has no scientific impact, but it's one of the coolest things we've produced from the image. So thank you for coming out today.